Hi there, here's a video on applying properties of matter to the 5-string banjo. And the 5-string banjo is called a 5-string banjo because, you guessed it, it has 5 strings. But the thing to notice is this weird 5th string that starts halfway up the neck. And the other 4 strings are right here on the back. And there's my tuner. So we're going to apply knowledge of properties of matter to this machine system. And it's a pretty interesting system and one of my favorite systems, one of my favorite machines. And it truly is a machine. It has a bunch of components that work together to do something. Just like an airplane is a machine, or a motorcycle, or a cell phone, or a kitchen sink. We're going to keep discovering that pure substances like metals and wood and things like this all have chemical and physical properties that can help us identify them or figure out what we can use them for. So properties of matter determine use or function. So I'm going to give you a little tour of the 5-string banjo. Pause the video and read the big ideas, and we'll get started when you're unpaused. So let's start off with the obvious. This thing is made of stuff, therefore it has mass, and we could measure that mass, perhaps in kilograms. And because it has mass, the Earth's mass pulls on that mass. So the Earth pulls on the mass of this banjo with a measurable force called weight, and it's heavier than it looks. It's about 15 pounds. And the reason it's so heavy is because of a very dense piece of bronze that wraps around the inside here, and that piece of bronze is called a tone ring. So the tone ring, you hear the sustain on that. The tone ring is made of bronze, so think of this thing as sort of like a round guitar mixed with a snare drum with a bell inside. And you hear the sustain on this. And banjos that don't have a tone ring like that don't resonate the way that this one does. The big hollow empty piece here, which is called the resonator, kind of like that piece on a muffler of a car, helps it resonate as well, and you can hear the effect of that as I talk into it. It's kind of like yelling in a stairwell. You get really cool acoustics. So mass and weight and volume apply. This thing is made of matter, so the matter takes up space, and therefore the thing has volume. And the people that designed my banjo case knew exactly how much space it took up so that they could make an empty space inside so I can put it in there and carry it around. Malleability relates to the finger picks here, which have to be flattened and shaped so they can form fit against my fingers. And then there's a little piece of plastic here on the thumb pick that's riveted to the metal. And this little piece here has to be malleable so that it can be shaped and my hand can sit on it. Thank you, Pluto. And this little piece here, called the flange, is also malleable, as are most of the other pieces. The tone ring inside has been shaped because of malleability as well. Ductility allows me to put metal strings on this thing, and without the strings, obviously, the banjo would be very boring. So this metal that makes up the strings can be stretched into wire, and then the wire can be wrapped around the tuning pegs. And you can adjust it to a certain tension, and you can get certain notes. Obviously, the strings have a certain tensile strength, and if I turn the tuning pegs a little too hard, I could possibly snap a string, so I have to be careful. Density I mentioned before in terms of this tone ring. The tone ring is made out of bronze, which is copper and tin mixed together. So bronze is actually a mixture, believe it or not. And you melt these two metals down and mix them together and then freeze them again. And you can shape it in the forms of bells and the tone ring that's in this banjo. But it's very, very dense. There's a lot of matter packed into this tone ring. And that gives the banjo a lot of weight because it has a lot of mass. Electrical conductivity. My little tuner here works because it's battery powered. And That's a good example of the conductivity of different materials inside the tuner. And if you look closely here, you can see a pickup, and it's a little plug. And if I want to plug into a big amplifier, I can if I want to. Thermal conductivity works, or is related to this banjo, because heat will pass through different materials at different rates. So if I touch the metal, it feels cold, because metal has a very high conductivity, a very high thermal conductivity. It steals heat from me very, very rapidly. If you touch like the metal on a pole outside in the winter, you'll feel this. You'll feel the pole pulling heat out of you. Different parts of the banjo don't feel as cold because they don't pull heat out of me as quickly. And even though this feels cold and this does not, they are both the same temperature because they've been sitting in this room for a long time. Another aspect of thermal conductivity is if I keep this banjo in a really warm place or play near a campfire or something like at Camp Mason, it will go out of tune because the materials will absorb heat at different rates. And the same is true if I keep it in the trunk of my car on a really cold day. Heat will flow out of the material into the surroundings at different rates, and it could damage the instrument. So a good rule for instruments is never put the instrument in a place where a human being would be uncomfortable. Cohesion obviously holds this thing together, so we're not going to talk too much about that. Cohesion is usually a property that relates to liquids. Brittleness is a little boring, but this wooden piece at the end is called the bridge, and sometimes that can shatter if you don't replace it. Texture, obviously this piece is very smooth because I'm moving my wrist all over it when I'm playing at different parts of the banjo, and the wood is polished here on the neck, so I guess banjo necks that were made out of sandpaper and broken glass didn't sell too well. I guess we won't be talking about melting point, but nor will we be demonstrating it. So let's just move on to luster. Obviously, the metal has a high luster. You might even see some reflections in it as I move it around here. But the more interesting aspect of luster is these iridescent inlays in the neck of the instrument. And these are made of a material called mother of pearl. And you see that they reflect light in a really cool way, the way that pearl earrings might. And these are made out of oysters and other sea creatures and things like that. And then they're polished up and treated so that they form all these really cool things called inlays. And expensive instruments have really cool inlays to give them more value and to make them cooler to look at. So that's luster. The tone ring that I mentioned before is made out of bronze, and the way that you get bronze is you take copper and you melt tin into it, and then you freeze it. So the tin actually dissolves in the copper, and that's how you make other alloys like stainless steel or steel. Steel is an alloy that has carbon dissolved in iron, and then it's frozen again, and it ends up being much stronger. Stainless steel has carbon and iron mixed together with additional ingredients to prevent the rusting on the outside. So ability to rust is pretty obvious. Some of these metal parts will rust if they react with oxygen. And ability to corrode is interesting because if you look at my strap here, you'll see some corrosion has formed around the edges of this little screw button thing. And another thing I have to be careful of is after I play, I tend to sweat. So a lot of the sweat and the salt in my sweat and the oils in my skin will react with this metal material, and it will form a new substance, and it will corrode. So I typically have to polish it when I'm done using it. And I guess we'll end by not talking about ability to burn. And I'll just refer you to my shirt here. And I'll play a little bit for you. Thanks for watching.